Hi everyone and welcome back to my channel A in Economist. So in today's video, what we are going to do, we are going to update our time series analysis playlist. So if you are someone who has watched all the theoretical videos that I have uploaded previously, then you will have a very good conceptual knowledge of what is time series analysis and forecasting. So today we are going to solve some questions and you will be glad to know that I'll be solving ISI questions, right? The questions which ISI Masters student do, and also the questions that has come previously in the PhD entrance examination. So many of you were telling me that you should make videos on JRF Economics and MSQE Economics. So I have given a thought to that and I have decided that I will solve some of the problems of ISI JRF Economics and MSQE Economics and put it, there in YouTube and make detailed playlist on that. And also, I am planning to launch a JRF course and a JRF workbook. So many of you were asking me to take, separate classes for JRF Economics and make separate playlist for that. So I have decided that I'll do that and I'll collect all the questions and answers, the past year questions and answers, and make an entire workbook for that, so that you can study on your own and get all the questions and answers done in a separate book. So if you are someone who is preparing for master's entrance and PhD entrance for specifically for ISI exams, that will be a very, very good resource because no such resource is currently available in the market. So if you want me to make a separate workbook and make a separate playlist on JRF Economics, then you can comment me below that yes, we want it, and I'll take actions on that, right? So with this, let us start with this question. This is ISI JRF Economics. JRF is basically the PhD entrance course that ISI conducts. So ISI JRF Economics from 2023 paper from the QEB section. QEB is the second paper, that is the descriptive section. This is question number 5. So let's take a look at this. We will solve part 1 in this particular video and we will go into part 2 in the next video, right? So with this, let us try to solve this question. See, let YT be a time series process which is given as this, right? This is a time series process. YT is phi YT minus 4 plus epsilon T. Now, epsilon T follows a white noise process with mean 0 and variance sigma square, where mod phi is less than 1. This is given to you. So, epsilon T follows a white noise process with mean 0 and variance is sigma squared. So basically, previously you should have a theoretical knowledge. I have made a detailed playlist. If you're new to my channel, you can see the detailed playlist before going into the question. This is kind of a revision session. We will apply the knowledge that we have already gathered theoretically, right? So epsilon t follows a white noise with mean 0, variance sigma square, and mod phi is given to you as less than 1. Then see the first question. The first part is asking you, is the process covariant stationary? Prove your claim, right? So this is part A of this question. Let us try to solve this portion first. So YT is phi YT minus 4 plus epsilon T, where this epsilon T follows white noise with mean 0, and this information is given to you. Now, what you can do is from here is that you can write this yt minus 4 to be L to the power 4 yt. This is the lag operator. If you remember, we have previously worked with this operator. So this is that. Now, what you will do, you will take this yt on the left hand side. This will be 1 minus phi L to the power 4 yt. And here you have the epsilon t as it is. Let me write L is the lag operator. L is the lag operator. So now this entire expression, entire expression will be the characteristic equation. So it can be written as capital phi L. See, it is only a function of L. So it will be capital phi L and the rest of the things are as it is into yt equals to epsilon t. So this is the equation. Now for a process, if you remember, for the process yt to be covariance stationary, for a process yt to be covariance stationary, we want all the roots of phi z equals to 0 to lie outside the unit circle, right? So if you have seen my videos, theoretical videos, then you will know I have explained this in details, how this statement is coming and what is the application of that. So I am not going to explain how we are getting this expression. So if you haven't watched those videos, please check the playlist out. I'll give the link in the description and also in the I tab button. So please understand this thing before going into the problem, right? So here I'll directly apply this thing. So phi z is equals to 0. If you do that, see, the characteristic equation is 1 minus phi L to the power 4. So it will be simply 1 minus phi Z to the power 4. Instead of L, you are putting it to be Z. Then Z to the power 4 will be simply 1 upon phi, which is strictly greater than 1. Why this is so? Because mod phi is less than 1. So what will be the absolute value of Z? This will be 1 upon phi whole to the power 1 upon 4, which will be again strictly greater than 1. So this basically tells you the process yt is covariance stationary, right? The process is covariance stationary, and this is how you check the first portion. And not only that, it is an AR4 process. If you see the structure, in the question, this is the model. So see, the maximum lag value that is here is 4. So that is why it is an AR4 process, and the own lag value, not the epsilon terms. The own lag value, the maximum value is 4. So it is an covariance stationary process and it is an AR4 process. And this is how you solve the first part of this question, which is part A. I hope this thing is absolutely clear. So you need to check this particular condition, that all the roots, see here, all the roots lying outside unit circle means every root is greater than 1. That is what we proved here. All the roots of the characteristic equation, which is this absolute value of z, it is strictly greater than 1, which basically means that the roots lies outside unit circle, which in turn means that the process is covariance stationary, right? So this is the first part. So the first 2 marks is done. Now let us look at the next part, which is the main question here, that find the autocorrelation function of the process y, right? So you have to find out the autocorrelation function. So let us try to do that. This is part. The autocorrelation function is simply ACF. So how do we proceed? See, yt is phi yt minus 4 plus epsilon t. So again, 1 minus phi L to the power 4 into yt is epsilon t. Now what we can do, we can simply take this 1 minus phi L to the power 4 in the inverse fashion, and then you can write epsilon t. Now what will be the expansion of this? What will be the expansion of this? So if you know this fact that 1 minus x to the power minus 1 can be written as 1 plus x squared plus x cubed plus so on and so forth. So if you apply the same logic here, this particular expression can be written as 1 plus phi L to the power 4 plus phi square L to the power 8 plus phi cube L to the power 12 and so on and so forth. Or let me write it in this fashion. Phi L to the power 4 and a whole square of that. Phi L to the power 4 and a whole cube of that, and so on and so forth. And then epsilon t term is as it is. Now, if this is the scenario, you can write yt, you can express yt in terms of only epsilon t. So the first term is epsilon t, just multiply. The second term is phi and then epsilon t minus 4. Because see, here you have L to the power 4. So it will be epsilon t minus 4. Then you have phi squared, epsilon t minus 8 and so on and so forth. So this expression basically expresses yt in terms of only epsilon t's. right? Yt only in terms of epsilon t. Now, if you have this particular form, you can find out what is the variance. Variance of yt. Variance of yt, which is simply gamma naught, which will be simply variance of the entire thing. Epsilon t plus phi, epsilon t minus 4, right? Pi square, epsilon t minus 8, so on and so forth. So variance of epsilon t plus phi square, variance of epsilon t minus 4 plus phi to the power 4, epsilon t minus 8. Now, what will be variance of epsilon t? That is simply sigma square. Why this is so? See, epsilon t follows white noise with mean 0 and the variance sigma square. So for all t's, for all the values of t's, the variance will remain sigma square. So this is sigma square plus you have phi square into sigma square. This is also sigma square. This is also sigma square. This is also sigma square. And this process continues. So pi to the power 4 sigma square, so on and so forth. So you can take this phi square out. 1 plus phi square plus phi to the power 4. So it is an infinite GP. So it will be simply 1 upon 1 minus phi square, where mod phi is strictly less than 1. Right? So this is how you find out the first thing, which is the variance of epsilon t. Right? Now let us move to the second point, which is gamma 1. Gamma 1 is simply covariance of yt minus 1. Now if you substitute the values, yt is epsilon t plus phi epsilon t minus 4 plus phi squared epsilon t minus 8 plus so on. And yt minus 1 will be simply t minus 1 pi epsilon t minus 5 pi square epsilon t minus 9 and so on and so forth. Now, if you look at all these expressions, there is no common term, right? There is no common term. So covariance are between all the uncorrelated objects because the non-autocorrelation thing is valid here. So epsilon t minus 1, the covariance is 0. Similarly, for these things, covariance, all the terms, they are different from each other. Covariances will be 0. There is no common term. If there is one of them is a common term, then you can express that in terms of variance and do something. But here, there is no scope for that. So gamma 1 is 0. Now, if you do this for gamma 2, you will see gamma 2 will also come out to be 0 because there is no common term in case of gamma 2. Similarly, gamma 3 will also come out to be 0. Now, the next term, you will have a term in case of gamma 4. Gamma 4, it depends on the lag value. So, see, gamma 4 will be what? Covariance of yt minus 4. So, covariance of epsilon t plus phi epsilon t minus 4 plus phi square epsilon t minus 8. And then you have epsilon t minus 4, pi epsilon t minus 8, pi square epsilon t minus 12, so on. Now see, there is a common term here and here. Here and here, you have a common term. So common terms will be there. Now, since common terms are there, you can, separate them out. The first term is this. Phi and then covariance of epsilon t minus 4. T minus 4 is variance of epsilon t minus 4, which is simply sigma square. The next term will come out to be phi cube sigma square. The next term will be phi to the power 5 and then sigma square, and this process continues. So take this out, 1 plus phi square plus phi to the power 4, so on and so forth. So phi sigma square upon 1 minus phi square, mod phi is less than 1. So this is about gamma 4. This is how you find out the covariance when the lag is 4. Now, this process will continue. Gamma 5 will be 0. Gamma 6 will be 0. Gamma 7 will be 0. Again, you will have a positive thing in case of gamma 8. So this is the last thing that we will do. Gamma 8, let's do that. Covariance of yt minus 8. So as you can see, so for the first value h equals to 0, there will be a covariance. There will be autocovariance function. For lag 4 you will have, for 8 you will have, and so all the multiples of 4. So in case of all the multiples of 4, you have some positive things. So let us see one more time. Pi square epsilon t minus 8. And here you have t minus 8 pi epsilon t minus 12 plus pi square epsilon t minus 16, so on. So what are the common terms? Here you can see this is the first common term you have. If you calculate, this will be phi square sigma squared. Next term is phi to the power 4 sigma squared. The process continues. You will take out 1 plus phi squared plus phi to the power 4 and so on. So it will be phi square sigma square upon 1 minus phi square. Where again mod phi is less than 1. We can use this representation because mod phi is less than 1. Now, if you combine all the things that we have done so far, if you combine, then the autocovariance function will be simply gamma h, which is given by gamma h when the lag is 0, which is simply this 1 minus phi square. This is the variance that we have got. For h equals to 0, gamma 0 is the variance. This is the expression for the variance that we have got. Now for all the other multiples, see, this gamma 0 is done. We don't need it so again. So for gamma 1, gamma 2, gamma 3, they are 0. So no need to consider that. Now see, for gamma 4, here you have phi to the power 1, sigma square 1 minus phi square. Find the pattern. Here see, the phi power is 1. Now for gamma 8, the phi power is 2, right? So when the lag is 4, the power is 1. When the lag is 8, the power is 2. So if you want to generalize this thing, what you will write in this way, pi to the power j sigma square upon 1 minus phi square when h is plus minus 4j and j is 1, 2 and so on. So this is the basic trick here, and 0, it will be otherwise. I know it might seem a little difficult for many of you, but ISI has separate standard for itself, and you have to get prepared with these kind of questions, right? So this is the autocovariance function. Now the question has asked you to find out the autocorrelation function. How to find out autocorrelation function? Then autocorrelation function. Autocorrelation function is given by rho h, which is the gamma h upon gamma 0. For covariant stationary process, this is something known as the autocorrelation function. Again, we have already discussed this in our class. So please check that out. So the first thing, when h equals to 0, gamma 0 upon gamma 0, so this will be always equals to 1. For any covariant stationary process you take, this will be 1. Now the second thing, see, when h is plus minus 4j, it is pi to the power j sigma square 1 minus phi square. So it will be divided by this particular expression, sigma square upon 1 minus phi square. So sigma square 1 minus phi square will cancel out. See, this is the common term in both these expressions. So the only term left will be phi to the power j. 4j and j is from 1 to so on and so forth, and it will be 0 otherwise. Right? So this is the answer for 5 part B. This is our required autocorrelation function. Right? This is our required autocorrelation function, and this is how you solve part B of this question. So we have solved 5 part 1. Under it, we had 2 questions, and we have solved each of these questions. Right? I hope you like this explanation. And in the next video, we'll be solving the next part of this question. And as I've told you, if you are interested in pursuing this course and you want to know more about this, you can write me down in the comment section that yes, we want a workbook and we want a playlist also, and I'll take actions according to that, right? So thank you so much for your time, and let's meet you in the next video.